Okay, so let's take a look at what the implementation for stacks and queues would look like. Specifically, we're going to start with stacks because they're actually simpler than queues to implement. And we're going to do this in terms of pseudocode. So this is not tied to any particular programming language, but these implementations could be implemented in any language of your choice that supports object-oriented. That's the variety I'm going to be working on. So these are going to be OO solutions. So let's look at the array version first. So with an array version, with a stack, we're assuming that we are going to start at the beginning of the array and it's going to grow towards the end of the array. So I am going to create a variable called top for myself. And I'm going to initialize it to be -1. So this is an invalid index in most languages. It's not in Python. But ideally, you want this to be some kind of an invalid index. You can set it to be whatever you like. But I want to be able to tell if my stack is empty or not. And so I'm going to use the value -1 for that. So to read, I'm going to, so if the top does not equal -1, I'm going to return the top of the array. However, otherwise, I'm going to return null or some other void thing. Okay. And if I'm going to insert an item, I also want to make sure that there's room. So if it's not full, so I haven't defined this yet. I'm going to define that in a second. So if it's not full, then I'm simply going to add 1 to top, and I'm going to add the new item at that location. Done. Otherwise, I'm going to print an error. And again, this is pseudocode, so I'm not going to put in all the details. But I'm going to, if it's full, I'm going to print out some error indicating that our data structure is full. And the reason why is because this is a fixed sized implementation. Fixed size array size doesn't change. Okay, now I haven't defined is full yet. So let me put that somewhere where we can fit it. I'm going to define a function is full, which simply returns if we're at the end. So if it's full, it means that top is now, if we're full, the top is equal to the length of our array -1. So if I'm at the last element of the array, we're full. Okay. So now to remove, I don't have to worry about removing. And really, in essence, this is peak. And this is pop. And this is push, because we're in stack land. But what I like to do is kind of keep these names consistent across all the data structures. But with a stack, it's peak, pop, and push. With a queue, it's NQ, DQ, right? And so there's different ways that we can interpret these names. So if I remove, I am going to, item I is going to equal, actually, we don't need a separate variable for this because we're not actually going to delete the item. We're just going to move top. So we are going to subtract 1 from top and simply return, oops, but wait, haha. I did forget about one thing. We need to make sure that it's not empty. If not is empty, then I'm going to subtract 1 from top and return array top plus 1, whatever the former top was. Otherwise, I'm going to return null. I could create a variable and initialize it to null and then only change top if it's not empty. And I'm doing it in this order of top minus minus and then returning, because after I return, I can't keep executing in the function anymore. So the only chance I have to change the value of my top pointer, my variable that stores our index of the last element of our stack, is to do it before I return. And so that explains that order a little bit. Okay. And finally, I want to do a search. So and this is going to return a true or false if it's in there. It could also return the index, right? So for I in, actually I can't do for I in array like I would in Python, because our array size might be bigger than the amount of data we have. So I'm going to say, for I can do for I in a range. For I in the range 0 up through and including top. So I'm using mathematic range notation here. I'm going to return true if I equals item, and if I get through the whole loop and I don't see it, then I'm going to return false. Okay, so that's what it looks like for an array implementation. Now, before I move on to linked list, what I would like to do is briefly show you how this implementation changes if we have a resizable implementation, because this one, there's not going to be any change, because linked lists are always resizable. For an array, though, there is going to be one change. No change. No change. I guess it might be clear if I just said same. Same is fixed. Same as fixed. Removing, same as fixed. Searching, same as fixed. The only one that changes is insert. So notice when we inserted before, let's see if I can do this. I want to copy that. All right, we're going to paste that. Okay. Okay, so this is what we were doing before. If it wasn't full, we added the item. Otherwise, we had an error. So we don't have this error anymore. And so really what we need to do is we need to change things around just a little bit. So we're going to keep this, but if it's full, we're going to do something. And if it's not full, we're just going to move these lines down a little bit. Uh-oh. I got my lines too close. Let's try this. There we go. So we're going to just put these down here. That's going to happen no matter what now. Okay, so if it's full, we want to make it bigger. So we're going to make a new list equal to the length of our array times 2. So we're going to double the size of the list. And so for I in, we're going to copy over the old ones. So for I in the range of 0 to the length of the array minus 1 inclusive, new list I equals array I, and then I'm running out of room. Right here, we're gonna, oops, let me make sure our arrow is right where we want it. We want this to be right here. Then we're gonna say array equals new list. Okay, there we go. So that, all of these 3 lines is what's happening. I wonder if I can try and move that up another time. But we're going to set our array equal to that new list, and we're going to copy everything over manually. And so that's how we make our stacks and our queues resizable. But nothing else changes. That's it. Just the insert. And think through it for yourself. Double check that you intuitively agree that only insert needs to change. Okay, so that's our completed stack implementation for array. And now let's take a look at the linked list. Okay, so we're going to start off with an empty list. Our head equals null. And linked list implementations for stack are pretty nice. Because if you think about it, a linked list where you add and remove everything from the head, a linked list is already kind of a stack. So for read, we're simply going to return the head. If the head is null, we return null, just like we did for reading in the array. And if it's something, we return that something. Okay, insert. Same things we used to do for adding an item to an array list. So we're going to say item. So I guess we would let's create a node. We'll assume we'll assume the item is not of type node. And we'll just say node n equals new node. It's pseudocode, so I can use whatever language I want. And we're going to say item, and that it points to head. And then we're going to say head equals n. Done. For remove, this is also pop, so it's destructive. I'm going to say node n equals head. Head equals the next node in the list. And I'm going to return n. Now, there is one little thing I should probably take care of. And that is, what if head is null and our list is empty? In that case, I might have to move these things over a little bit. So if our head does not equal null, I am going to move this over just a little bit. Okay. And there's a last little piece of information we have here. We have a search. I'm sorry, I don't know if you can hear that on the recording. I have a little cherub in the background. Not right now, sweetie. Okay, so we're going to return true or false for our search. And so what does the search look like for a linked list? So we're going to create a node equal to the head, and while n does not equal null, if n.data equals our item, we're going to return true. Otherwise, we're just going to keep setting n equal to n.next. And if we don't ever see the item, then we're simply going to return false at the end. And there you have it. And as we already said, if we for a linked list implementation, stack implementation, fixed and resizable, it's always the same because a linked list by its very nature is always resizable.